section 7.5 is going to be the last section that's on the gateway. So like I'd mentioned in class, 7.4, which is all about trig substitution, is not on the gateway, which is a good thing, because as you'll see, those problems tend to be a little long. So we're going to go back to 7.4 after the gateway and talk about how to do those types of problems. All right, so partial fraction decomposition. So this is really just an exercise in algebra. The integrals that you do are very straightforward once you get the algebra done. So think back to whenever you learned how to put rational functions like 1 divided by x minus 1 plus 5 over x plus 3 together. So you would put these together by getting a common denominator. So we would say, okay, I'm going to multiply the 1 times x plus 3 plus the 5 times x minus 1 all over, x minus 1 times x plus 3. And then distribute all this stuff out. Well, the 1 doesn't really do anything, so we're going to have x plus 3 plus 5x minus 5 over x minus 1 times x plus 3. And combine any like terms. So I have 6x minus 2 over x minus 1 times x plus 3. So this is not what we're going to be doing. We're going to be doing the reverse direction. So in other words, if I start off with, say, x plus 8 divided by x minus 1 times x plus 2, how can I break this apart into something that looks like this? It's probably the worst question mark I have ever written. Okay, so that's the plan, because what's going to happen is we're going to have an integral here, and it's going to be a lot easier to integrate these two things because these will just be natural logs. So like I said, that's what this whole idea is the integrals will be very straightforward once you break it apart, but it's just going to be an algebra trick. So this section is all about algebra. The process of partial fraction decomposition is broken up into 4 cases. One of the cases we're not going to do because it's literally an algebra nightmare. But in increasing difficulty, we're going to look at how to deal with distinct linear factors, how to deal with repeated linear factors, and how to deal with irreducible quadratic factors. The 4th case is repeated irreducible quadratic factors, and it's a nightmare. So we're not gonna deal with that. So let's take a look at this first example. So we want to integrate x plus 8 over x minus 1 times x minus 2. So what we mean by distinct linear factors is I have 2 factors in the denominator, and these are linear, and they are distinct, meaning they are different. So we don't have like an x minus 1 times an x minus 1, because that would be x minus 1 squared, and that's a repeated linear factor. So we'll look at how to deal with that in a minute. Okay. So the first step is going to be take your integrand, so the guy that's inside of the integral, the function, and let's just write them, say, down here. So x plus 8 over x minus 1 times x plus 2. Going back to what we were talking about up here, we're trying to rewrite this, and we want to figure out what these numbers are. So instead of using question marks, we're just going to use some letters. So I'm going to say a over x minus 1 plus b over x plus 2. Okay. Now, we want to clear out the denominator. So you're going to multiply both sides of this by x minus 1 times x plus 2. So on the left-hand side, we're going to have x plus 8. And on the right-hand side, all that's going to be left is we'll have a times x plus 2 plus b times x minus 1. So the step that we did here is you're going to clear out the denominators. Okay. And in fact, let's make this a different color so we can keep track of what's what. All right. Now you want to pick convenient values of x and plug them in. So remember, we're trying to figure out what a and b are. So what we're going to do is say, okay, I noticed that if I plug in 1, that'll kill off all of this, and we can figure out what a is. So when x is 1, on the left-hand side, we'll have 9 equals 3a. So this tells me that a is equal to 3. We'll keep track of that. Now we're going to plug in x equals -2 to kill off the a term. So x equals -2. I'll have, well, -2 plus 8 is 6. The a term goes away, and we'll have -3b. So this tells me that b is equal to -2. So again, this step that we just did here is you're going to pick some nice values for x. Okay. Now we're good to go. Because our integral that we're interested in, the x plus 8 over x minus 1 times x plus 2 dx, this is equal to the integral of a divided by x minus 1, so 3 divided by x minus 1 dx, plus the integral of b divided by x plus 2, where b is -2. So -2 divided by x minus 2 dx. And now you're good, because we can just integrate. Each of these are just a log, and this is what's usually going to happen. So we'll have 3 times the natural log of the absolute value of x minus 1, plus a -2, so -2 natural log of x minus 2, plus c. And there you go. So there's how you do the distinct linear factors type of partial fraction integral. Like I said, it doesn't matter if you had a whole bunch of linear factors, if you had stuff, whatever it is, times x plus 1, x plus 2, x plus 3. How many of these you have, it doesn't matter. You're going to have a over x plus 1 plus b over x plus 2 plus c over x plus 3, right? So if this just kept going, right? You just plus yada, yada, yada. And then, so you would have 3 different lines here instead. You just pick 3 different convenient values, figure out what a, b, and c are, and they're all going to integrate to be logs. So next up, we'll take a look at how to deal with repeated linear factors. So it works pretty similarly. There's going to be one slight difference, but other than that, it's not so bad. In the previous example, the denominator was already all factored. We had, what was it? It was already factored for us, the x minus 1 times x plus 2. So a lot of times, the denominator is not going to be factored. So if you look at something like this, just go ahead and factor the denominator before we even get started. So we'll have 3x squared plus 5x plus 3 in the numerator, and then just factor an x squared out of each of these. Okay. And this is what it means to have repeated linear factors. So we have a distinct linear factor right here, and then we have a repeated linear factor right there. So we have x times x. That's a repeated linear factor. So how we're going to do this is we're still going to set it up basically the same way. So we're going to have our integrand. So 3x squared plus 5x plus 3 over x squared times x plus 1. For our distinct linear factor, for the x plus 1, you still do what we did in the previous example. So we're going to have a over x plus 1. And now for the repeated linear factor bit, every factor of that repeated linear factor gets a fraction that sort of looks like this. So we're going to have plus b over x, and then plus c over x squared. If this were, an x to the 5th, you would have to have a d over x cubed, e over x to the 4th, etc. However many of these repeated linear factors you have, they each get a little fraction that looks like letter over the factor. Now what we did before is still going to hold true. So you set up your little fractions like this, and then clear out the denominator. So you want to multiply both sides by x squared times x plus 1. On the left-hand side, everything in the denominator will just cancel. So we're going to have 3x squared plus 5x plus 3 equals a. Now, if we hit this fraction with the denominator, the x squared x squared times x plus 1, the only thing that's going to be left is we're going to have a x squared. And then same thing here. We'll have bx times x plus 1 And then here we'll have c times x plus 1. Yeah. And then, yeah, just double check. So yeah, if this was, so the x plus 1 would go away. This would lose the x, giving us that. Yeah, so we're good. It's always a good idea, just double check, because you don't want to go through, this is going to be a slightly longer process, and you don't want to go through all of that and then end up with the wrong answer in the end. So just always double check. All right, so what we did before is we had something that looks something like this, and then we picked some nice values of x. So the same thing's going to be true here. If I plug in 0, then the a term is going to go away, and the b term will go away. So on the left-hand side, we're going to have 3 equals, and plug in 0 over here, so we get c. So this tells me that c is 3. What else could we plug in? We could plug in a -1. So if I plug in -1, on the left-hand side here, what do we get? This will be a 3, this will be a -5, and this will be a 3. So I have 3 plus 3 is 6, minus 5 is 1. The b term will go away because of the x plus 1 factor, and the c term will go away because of the x plus 1 factor. So we just have a, because -1 squared is 1. So a equals 1. Now we run into a problem. There are no more nice values of x that we can plug in to figure out what b is on its own. So what you have to do in this case is pick another nice number for x. So I'll just say 1. It's a nice number. And what we're going to do is we're going to plug in x equals 1 and c equals 3 and a equals 1. And then we'll be able to figure out what b is. So if you plug in 1 on the left-hand side, you'll have 5 plus 6, which is 11, equals a, so let's just do it in steps, times the 1, plus plug in 1 into these two pieces, gives us what? 2b, plus, again, plug in 1 into the c term, gives us 2c. Okay. But we also know that c is 3 and a is 1, so let's plug those in. So 1 plus 2b plus 2 times c, so 2 times 3 is 6. Okay, now solve for b. So subtract 1, that gives us a 10 on the left. Subtract 6, that gives us a 4 on the left, equals 2b. And last step, b equals 2. Okay, so we figured out what a, b, and c are, so now we're good to go. So our integral, which I don't want to rewrite it, we'll just call it I. So our integral I is equal to, what did we have? The integral of a over x plus 1, so the integral of a, which was 1, x plus 1 dx, plus the integral of b divided by x. We just found out that b was 2. So 2 over x dx, plus the integral of c divided by x squared, and c was 3. So 3 over x squared dx. Well, the green integral, that's just a natural log of absolute value of x plus 1. The purple integral is 2 natural log of the absolute value of x. What about the orange one? Well, we would say, okay, pull the 3 out. This is x to the minus 2. And then just power rule that piece. So let's just rewrite this stuff. And what are we going to get? We're going to add 1 to -2, so now it's -1, divide by -1, so this will be a minus 3 over x, plus our integration constant. Not to be confused with the c that we had up above. Okay. So that's how you deal with repeated linear factors. Again, you're going to set up the easiest mistake, I guess I should say, is remember every power of your repeated linear factor needs to get one of these fractions. You're going to have a letter over the factor to that power. So just be careful. And be careful with the arithmetic. That's also going to be kind of the downfall. But that's how you deal with that one. And one more example, we'll deal with how to deal with distinct irreducible quadratic factors. So it's a mouthful, and it's a slightly different process, but it's just algebra. All right, so last case to look at that we're going to do, and as you'll see after we do this example, this is enough algebra. If we did the other one, which is the repeated quadratic factors, it's a nightmare. So let's take a look at this monstrosity. So we have this gigantic integral of this rational function that we want to do. So what we mean by irreducible quadratic factors is this guy right here. X squared plus 4 cannot be factored further over the real numbers. So x squared minus 4 is not an irreducible quadratic factor because it factors as the product of two distinct linear factors. Okay, so we'll have things, like x squared plus a number, or you could have some other mixed quadratic thing. I don't know if that's irreducible or not, but it could be anything. But usually the problems just stick to x squared plus a number. Okay, the setup is still going to be kind of the same as what we just did. So let's go ahead and get that set up. So we're going to have 2x squared plus 23x plus 7 over our x plus 5 times x squared plus 4. So we have our x plus 5 factor, so that's a linear factor, so you still do what we did before. So we're going to have a over x plus 5 plus, now the thing that's new for our irreducible quadratic factor, you're going to set up a linear piece up in the numerator. So you're going to have plus bx plus c over x squared plus 4. Okay, so linear factors just get a letter. Repeated linear factors, every power of that repeated linear factor gets a letter fraction thing. And then the irreducible quadratic factor gets a linear piece upstairs, so we get a bx plus c. Now, we're still going to clear out the denominators like we did before. So we're going to have 2x squared plus 23x plus 7 equals a times x squared plus 4 plus bx plus c times x plus 5. Now, in the other examples, what we did is we started picking nice values of x so we can try to kill off some terms. You can do that here, but the issue is we can only kill off this term here, all this stuff, by plugging in x equals -5. There is no real number that I can plug into that'll get rid of that. So you could do it that way, but you're still always going to end up with a system of equations to solve. So what we're going to do instead is on the right-hand side, distribute, FOIL, get everything all collected, or get everything all expanded out, and then collect all your like terms. So we're going to have 2x squared plus 23x plus 7. Distribute the a, so ax squared plus 4a, and then expand out the bx plus c times x plus 5. So we're going to have plus bx squared plus 5bx plus cx plus 5c. Now, on the right-hand side, collect all your like terms, and I'm going to do something with all the coefficients just so we can talk about what's going on here. So I'm going to have 2x squared plus 23x plus 7. This is going to be equal to, collect all your x squared terms. So I have an ax squared and a bx squared. So that tells me I have a plus b x squared. Let's just get rid of these so we don't double up on them. Collect your x terms. So we have a 5bx and a cx. So that tells me I have plus 5b plus c x's. And then I have a 4a and a 5c. So plus, you don't need the parentheses here, but just for emphasis, I'm going to put them here. 4a plus 5c. Okay? And the reason why I'm color coding all this stuff is this equation that we have now, so this equation here, it is saying that I have one polynomial, the left-hand side, equals another polynomial, the right-hand side. And two polynomials are equal, so they're the same polynomial if and only if all of their coefficients agree. What that means is I get a system of three equations and three unknowns. The x squared terms tell me that a plus b equals 2. The x terms tell me that 5b plus c equals 23. And then the constant terms tell me 4a plus 5c equals 7. Right? So now we have the system of equations. Now, however you choose to solve these is going to be completely up to you. You could do all the elimination stuff they talk about in algebra, substitution, whatever. Okay, I'm just going to do the substitution stuff. It tends to be a little bit easier when you have factors that don't have coefficients and whatnot. So the red term there tells me what? This says that a is going to be equal to 2 minus b. The purple term tells me that c is equal to 23 minus 5b. And now what we're going to do is, since this orangey colored term has a and a c, but I know what a and c are from what we just did in the red and the purple, we're going to plug those in. So we have 4 times a, so 4 times 2 minus b, plus 5 times c, where c is 23 minus 5b. This equals 7. Now you have a linear equation. It's linear in b, so you're going to solve for b. So distribute the 4. So we have 8 minus 4b plus distribute the 5. So 5 times 23 is 115 minus 25b. And this equals 7. Okay, so get all the constant terms on one side, all the non-constant terms on the other. So move all the numbers to the right. That gives us negative 116. And then negative 4 minus 25 is negative 29b. Divide by the negative 29. So b is 4. Okay, so what are we going to do now? Well, I know that b is 4, and I know that a is 2 minus b. So this tells me that a is going to be 2 minus 4. So a is negative 2. I know what b is, so from the purple, I know that c is going to be 23 minus 5 times b, which is 4. So this tells me that c, helps if I write it, c is 3. Okay, so there's the algebra nightmare. But the process is always the same. You set up the fractions the way that we did before. So the linear terms get numbers over the linear term. And the irreducible quadratic factors get this linear piece upstairs. It's just going to be very, very careful when you're doing the mental arithmetic or the algebra. Okay, so now we're good. We can integrate now. Because our integral that we're interested in, and again, I'm going to be ultra lazy here, I, this is equal to, so I is equal to the integral of, what did we have? A over x plus 5, where a was negative 2. So negative 2, might as well just so you can see the colors, negative 2 over x plus 5 dx, plus the integral of bx plus c over x squared plus 4, where b is 4 and c is 3. So we're going to have 4x plus 3 divided by x squared plus 4 dx. And now we can integrate. This first integral is just another natural log. So negative 2 natural log of the absolute value of x plus 5. Plus, this second integral here, we have discussed how to integrate something that looks like this. It's not just going to be a u substitution where you let u be the denominator, setting it up for a log, because this purple plus 3 is going to mess us up. So the trick here was we're going to split apart the fraction. So you're going to have plus the integral of 4x over x squared plus 4 dx plus the integral of 3 over x squared plus 4 dx. Which gives us now, we'll have negative 2 natural log of x plus 5 plus this integral is another natural log. If you let u be the denominator, so u is going to be x squared plus 4, du is 2x. Okay, I have a 4x up there, so all that means is we're going to have plus 2 times the natural log of x squared plus 4. And again, x squared plus 4 is never negative, so we don't need the absolute value bars there. If you put them, it's fine, okay, but I'm just going to put parentheses there. This last integral is an arctangent, where a is 2 and my u is x. So plus 3 halves arctangent of x over 2 plus c. And there's our antiderivative of that monstrosity that we started with. Okay, but that's how the work will look. I'll try to get all of it up here so you can see it. Okay. Like I mentioned, there's another topic in this section where how to deal with repeated quadratic factors. So instead of that x squared plus 4 in the denominator that we had, if we had like an x squared plus 4, all of that squared. Just imagine. I mean, look how much work this was. It's even more than that. It's a disaster. So make sure to get those couple of questions. I think there's probably 3 since we talked about 3 examples in this video. Try to get those done, before class. Come to class. We're going to work on another 10 problems. So it's just practice. So have a good rest of your weekend, and I'll see you later.